Hi friends, I am Dr. G. Srinivasa Gupta, Professor, Department of Mechanical Engineering from VIGNANA JYOTHI, Institute of Engineering Technology. So today, as part of the Dynamics of Machinery course, we are going to discuss the concept on band brake and differential band brake. Basically, the difference between these two. Already in previous lectures, we have seen what is band brake, types of brakes starting from and coming to band brake, then differential band brake and band brake. As we know that band brake consists of flexible band wrapped around the rotating drum. When tension is applied in the band, friction between the band and drum leads to the braking torque, so that retard the vehicle. But in case of band brake, simple band brake it is also called. In case of this, the one end of the band is fixed to the frame, other end is attached to the lever. Okay, then the braking torque and tension ratios, all these we have seen applications also we have seen already. These are the applications. And tension ratio T1 by T2 equal to E power mu theta. T1 is tension at tight side and T2 is tension on slack side. Now coming to the differential brake. Differential brake is modified band brake, nothing but modified band brake, where both ends of the band are attached to the lever at a different distance from the fulcrum. It is not fixed, attached to the lever. Okay, it's like this. This consists of that lever consists of two arms, and this is the fulcrum, and one end of the band attached to the lever and other end is attached in some other location, not at pivot. Okay, this is the lever. Then we can have, this is the fulcrum, then drum. This band is wrapped around the drum. So when this drum is going to rotate clockwise, let us say, then the tight side becomes this one and slack side becomes this one, as we know that. Okay, in as it is in simple band brake, but the ends of the band are attached to the arms. It is not attached to the fulcrum. Okay, in case of band brake, one end is attached to the fulcrum, that is frame you can say, and other end is attached to the lever. Basically the lever consists of two arms in case of differential band brake. Due to this arrangement, the braking force can be increased or decreased automatically depending on rotation and direction of the wheel. Okay, here both ends are connected to the lever, produce a differential action, requires smaller effort compared to the effort we are going to apply the brake, that is very small enough than the band brake. Application wise, this differential band brake is concerned, we have machine tools, lathes and heavy duty braking system. But here also we can apply tension ratio T1 by T2, and T1 minus T2 is into radius of the drum is torque, braking torque. But the basic difference is, while you take the moments, then you can have the relation such that the effort required for applying the brake becomes less, and braking effort for less effort, braking torque becomes more in this case. Okay, we will take a few numerical exercise on each case, simple band brake and differential band brake. Let us see. Before that, if we compare these two, band brake and differential band, as you know that this connection, in case of band brake, one end fixed and one attached to the lever, one end of the band is fixed to the frame or fulcrum we can say, and differential band brake, both ends are attached to the lever. Okay, there is flexibility, and lever arrangement, single lever arm it consists, consists of single lever arm, and in the case of differential band brake, two differential lever arms, and effort required is higher in for same braking torque, higher in case of band brake, and lower in case of differential band brake, and mechanical advantage is higher in case of differential band brake. Okay, self-locking is very rare in case of band brake, and self-locking is possible. What do you mean by self-locking? which is without applying effort also, because of tension differences and movements, opposite movements, that will be itself will leads to application of the brake. Complexity, it is simple band brake and differential band brake, more little bit more complex as we have seen. Okay, I think you are able to understand. Coming to the band brake, as we have already seen how to analyze the band brake for given specifications. Okay, the power here in this problem, band brake is applied to drum 500 mm diameter, mounted on a shaft rotating 200 rpm. N is 200 rpm, drum radius is 250 mm because diameter 500 given. The power transmitted given 20 kilowatts. The angle of contact of the band is 210 with the drum, and the coefficient of friction is 0.3 given. Okay, so the brake lever length is 600, total length of the lever, and the distance of the band from the fulcrum is 100 mm. So what do you mean by this? So the distance from the band from the fulcrum is this lever. Okay, one end is attached to the fulcrum and other end is on the lever, as you know that this band, okay, here and here. This is the drum which is going to rotate, and here effort we are going to apply. Here what is this distance? 100 mm, distance of the band from the fulcrum. This is the band, because this band attached to the frame fulcrum itself, this is 100. Total length is this is the length of the lever is given, okay, 600 mm, okay, 600 mm, right. Then as usual, torque we can evaluate. P equal to power transmission equal to 2 pi nt by 60. From that we can get torque 955 Newton meter. And differential band tensions, always any problem tensions you need to calculate, because braking torque to estimate that is equal to T1 minus T2 by R1 relation. Second relation is e power mu theta, T1 by T2 equal to. So these two relations used to find the tensions. So braking torque we know, that's why we can write one relation, braking torque equal to T1 minus T2 into R drum radius. Then obviously T1 minus T2 we got 3820 newtons in this case, and T1 by T2 we can evaluate. Mu is given 0.3, and theta always we need to express in terms of radians. Okay, 210 degrees given, 210 into pi by 180, which will give 3.665. So we got T1 equal to 3 T2. So then we have previously relation T1 minus T2 is 3820 newtons. So we can substitute T1 plus 3 T2 from previous relation, T1 equal to 3 T2. Then we have T2 is 1910 and T1 is 5730. Okay, you want effort, then you obviously take the moments. This is a simple brake. Moments you need to take. This is the lever, fulcrum, one band, one end is attached, the other end is attached to the lever. Okay, this is effort P we are going to apply. This is the drum which is going to rotate. So obviously P into 600. If you take moments about the fulcrum, let us say this P into 600, and here tension, you know that tension on the okay, I am taking only lever. Then this is T1. Okay, on drum this is T1. Okay, this is T2 obviously, T2. Okay, moment of T2 about O is anyhow 0, it is passing through that O, and T1 into P into okay, P into 600 equal to T1. Okay, T1 into 100. So P equal to 955 newtons you have got. Okay, this is about the effort required at lever. Okay, that is P, right? Then if you come to the differential band brake, as you know that, okay, this is the drum and this is the band. Okay, both the ends of the this is two this lever consists of 2 arms, okay, like this. Then this is the pivot point, right? And this band, one end of the band attached to the lever here, and other end of the band is attached to the lever arm here. This is fulcrum, fixed frame point. Okay. Now here also we will take, this is rotating in the clockwise direction. Then tension, okay, T1 becomes this one. If your drum is rotating clockwise direction. then this becomes T2. So effort P, if you try to get the effort, then this diagram is this one. Then the tight side of the band is attached to the brake lever at a distance 40 mm from the fulcrum. This is 40, tight side, in this case 40, right? Are you able to understand? Then and the slack side is attached to 160 mm from the fulcrum. This is 160, right? Okay. So then the fulcrum on the opposite side. Okay, opposite side. One side is attached here, one end of the band is attached here, opposite side of the from the fulcrum. The effort is applied at the end of the lever. Lever length is 500 mm given. Total length is 500. Total length 500. You have to take like this. Okay. Then you need to determine effort required to apply the brake. If the braking torque required is 1500 Newton. Torque is directly given. The tension in the tight side and slack side also you need to estimate. So then this braking torque is given directly. Okay. Then relation between tensions, we know that T1 by T2 e power mu theta. Mu is given, theta is given. So T1 by T2 relation 1 we have. T1 by T2 we have some numerical value we will get. Then okay. That is we got 2.93 T1 by T2. Then braking torque is given. So braking torque is given. Braking torque which is known is T1 minus T2 into radius of the drum. Because radius of the drum we know 0.25 meters. Diameter is 500 mm. So radius is 0.25 meters. So obviously we will get T1 minus T2 is 6000 newtons. Okay. Then we have T1 by T2 is 2.93 and T1 minus T2 is 6000. We can find T1 and T2. But here in this problem, what is asked here? Effort required to apply the brake. Okay, tension on tight and slack sides, now we have estimated. That is second part of the problem question. And we have got T1, T2. Okay, T1, T2. T1 is 9109, T2 is 3109 newtons. So now if you want effort required, then you need to take moments. You can see now P into about fulcrum. P into about fulcrum. What is the distance? So this lever length is given from fulcrum. That is P into you can see P into 500. Okay, P into 500. About fulcrum it is said. Okay, actually this is the 500 given. Okay, this is 500 lever length. Okay, you need to take this first, this arm actually. Okay, P into 500 plus T2 into 3190. That is T2 into 160. This is T2 into 160. Because opposite these are. Okay, and T1 into here you can see T1 into that is 910 into 40. Okay, T1 into 40. Okay, these two are same direction moments about fulcrum, P clockwise and T2 is also clockwise and T1 is anti-clockwise. That's why it is written right side equal to 9109 into 40. Okay, this is the distance 40 from the fulcrum, the band at T1 side attached. So from this you got P equal to 266 newtons. That is negative value. The negative sign indicates direction of effort. Effort required in opposite direction. So these are all final T1, T2 and P values. So this is about all the difference between simple band brake and differential band brake, and the configuration is most important to understand, and accordingly we need to analyze the problem, given problem statement, and find the unknown quantities required. Okay, this is with this I am concluding here. In our next lecture we are going to discuss the balancing of rotating masses. Okay, okay, thank you, one and all.
Like, share, comment and subscribe VNR Digital Learning Resource YouTube channel.